Alright, in the previous video you have seen that I gave you the outline of our project, which will be completed in the next few weeks as the time permits. So in our first official lecture we will be dealing with the origin of quantum mechanics, which actually was a result of the failure of classical mechanics. So we will discuss that how there were certain experiments done by the pupil which were not explained on the basis of using the classical mechanics. So it was, I think, 19th century, during the up till the late 19th century, it was well established that the classical mechanics is the final subject as far as physics is concerned. Everything was thought to be explained on the basis of classical mechanics. But during the first half of the 20th century, few experiments were done by the pupil which were a blow for the classical mechanics. Classical mechanics had no option for that, had no clue for that, no answer to those very experiments. And few of them, which will be discussed in this lecture, were, for example, the black body radiation, the mechanism adopted by the black body, the radiation which is given out by the black body. First of all, I will discuss a bit about the black body, as you might be well aware about black bodies as well, but I will give a simple definition for that. A body which emits as well as absorbs all kind of possible wavelengths. Okay, all kind of possible wavelengths of the light, of the electromagnetic radiation. So a body which absorbs all kind of electromagnetic radiations as well as it emits at the same time. It can emit all kind of wavelengths possible. Okay, so people studied black bodies and they concluded the result that a graph was done which was drawn between the relative intensity. For example, this is a graph. Along this very axis they took the relative intensity of the light which is emitted from that very black body. For example, this is our black body. Okay, we make a sphere like thing having a hole there, and we put the incident radiations onto here so that it gets inside the cavity, and inside the cavity we put a little notch here so that all the radiations, almost all the radiations which are incident on this body get trapped inside this. Okay, all kind of photons gets trapped inside this. So this is a kind of ideal black body. So they studied bodies like these, and a graph was drawn between the relative intensity which was radiated by the black body, per se any body, but here under discussion is the black body. So if a graph is drawn between the relative intensity and the respective wavelengths of those very photons, this is the lambda, that is the wavelength of those very emitted radiations. So they drawn a graph experimentally. They found that with the increase in the wavelength we get a graph of the intensity of the incident of radiations like this at certain kind of temperature. For example, this was at temperature, say something 3500 Kelvin. We get a graph like this. For the black body radiation, for the black body, if it is heated or it is kept at a temperature of 3500 Kelvin, we get a graph like this. Then if we decrease the temperature, we get the graph like this. That means there is a little shift in the peak intensity for that corresponding temperature. Say this is 2500 Kelvin. Similarly for 2000 Kelvin, like this. Okay, so we get the graph for a black body like this. So what they studied, if we consider the classical mechanics to be true for this very black body radiation as well, we know from the classical mechanics, the wave theory of classical mechanics, wave theory of light, what does that say? Wave theory of light says that the intensity of any body, the intensity of the radiations which are emitted by that body is inversely proportional to the fourth power of the wavelength. Okay, because we know that the intensity in the classical wave mechanics is proportional to the square of the amplitude, and which in turn comes out to be inversely proportional to the fourth power of that very wavelength, of the corresponding wavelength. So if it is considered to be true that the classical wave mechanics is true for all kind of substances, and in that case black body also, then intensity should have been inversely proportional to the fourth power of the wavelength. That means, for example, they did the experiments, we get that very graph. So consider this very graph. Forget about this very part first. So we take the example of this very thing. Here is the peak value for that intensity. If we move from the peak value towards the right side, we get that with the increase in the wavelength, there is a decrease in the intensity like this. And that is in accordance with the classical wave theory. That is, with the increase in wavelength, there is a decrease in the intensity. Okay? But there was a catch. Experimentally, we got this very result. But if for this peak, for this value 3500 Kelvin, if we move towards left side, that is with the decrease in the wavelength, there should have been increase in the intensity as well from here moving towards this very thing, because with the decrease in the wavelength, it is inversely proportional to the intensity. So if we decrease the wavelength, there should have been increase in the intensity of the emitted radiations. So if for the sake of argument, if this would have been the graph, experimentally, if this would have been graph like this, okay, this should have been the intensity and this is wavelength. If with the decrease in the wavelength there is an increase in the intensity, then that means the classical theory was right. But there was a blow to it, that with the decrease in the wavelength, there is again a decrease in the intensity. You can see from the graph also, because if we decrease the wavelength, the intensity gets decreased, which is against this very thing, because it says that for lower and lower wavelengths also there should be an increase in the intensity, but that was not the case. So there was a catch here. This very part was against the classical wave theory, and that very is known as there was a kind of catastrophe. That means the disaster was seen in between the wave theory and the experimentations. Experiment and the wave theory, the theory was not in accordance with the experiments. So there was a catastrophe that for the lower wavelengths, for example, For the lower wavelength, if we consider the visible spectrum, we have visible spectrum like this. If this is the wavelength on this side, with the increase in the wavelength, okay, if we increase the wavelength, for example, consider the example of the waveguide. So red is the light which is having the higher wavelength, and violet in the visible spectrum is the spectrum which is having the lower wavelength, and the lesser than that is the ultraviolet. So experimentally it was found that as we go towards the decreased wavelength spectrum, there is a flop of classical mechanics, and that very thing is observed in case of the lower wavelengths which are under ultraviolet radiations, which are under the category of the violet and ultraviolet radiation. So this very thing took the name, it grasped the name from that, and this catastrophe is known as the ultraviolet catastrophe, UV catastrophe. Okay, so there was a mismatch between the wave theory and the classical wave theory and the experimentations which were done. So, and there came the origin of quantum mechanics, which was furthermore then elaborated by various people, and few of them were Planck, Wien, and others as well. For example, Wien gave a law, simple law in this very field. Consider this very diagram for the black body. Wien said that okay, if we draw this very diagram like this, for a particular temperature of the black body, say it is having temperature T, okay, for any particular temperature T, we will get a maximum intensity at a particular wavelength, this lambda. We will get a maximum peak inside the intensity for a particular wavelength having a particular specific temperature. So what Wien said, he concluded experimentally that if this is the corresponding wavelength at the maximum intensity, then the product of this very wavelength, which is the peak value for the intensity, the corresponding wavelength lambda m, the product of this very lambda with the corresponding temperature, that is T, for this very thing, it is always a constant. It's always a constant, and that very constant he represented as B. For this very experiment, this constant B is equal to 0.0029 meter Kelvin. So he concluded that if we consider the particle nature of, you will see to this very concept is a bit, you will see in detail in the upcoming classes, that if we consider the particle nature of the light now, then this very behavior, the graph, this very behavior, that for the lower wavelengths also there is a decrease in there is a depth in the relative intensity. This is explained only if we consider that light is a particle kind of thing. So there was Wien, he discovered a relation lambda max multiplied by time multiplied by temperature. For that specific value, for that specific temperature, we get a specific value that is constant, which is called as the Wien constant, and that very value is equal to this very thing. So there was a failure in explaining the experimental behavior of the black body, which gave later on the birth to quantum mechanics. Other experiments which were done, let me erase it first. Okay. Another experiment which was a kind of failure for classical mechanics to explain that very experiment. As I told you in the initial lecture, the experiment was, which is known as the photoelectric effect. Photoelectric effect. This experiment was also not explained, could not be explained if we consider the wave nature of light. So what this experiment actually says, that if we have a metallic surface, if a metallic surface is exposed to suitable frequency of light, then there will be an emission of electrons from that very surface. Emission of electrons. That is, if a bunch of photons is incident on this metallic surface, then with a suitable frequency, and that very frequency you will see that is called as the threshold frequency. So if a bunch of photons are incident on this metallic surface, there is a kind of ejection of the electrons from this surface, and that very phenomena, the ejection of the electrons, that very phenomena is known as the photoelectric effect, because these electrons, if we draw a circuit, they can there will be a kind of current inside the circuit, which is known as the photoelectric current, and these electrons are the photoelectrons. These are the photoelectrons. So what was experimentally observed there, that these electrons, they possess some kinetic energy inside them, and that very kinetic energy, the kinetic energy of those very photoelectrons was seen, it is proportional to the frequency of the incident radiations of the light. And this kinetic energy is independent. This is the most important thing inside it. The kinetic energy possessed by those very electrons is independent of the intensity of the incident light. That means, however, it doesn't matter what will be the intensity of the incident light, as much as it is having some frequency which is higher than the threshold frequency, there will be an emission of the electrons from the metallic surface, and those electrons will be possessing a kind of kinetic energy which will be independent of the intensity of incident light. This was the experimental data which was observed, that the kinetic energy is only proportional to the frequency of the incident light, not the intensity. But in the classical mechanics, we know if we consider the wave nature of the photons, if these photons would have been considered as wave, as it was thought to be, then there was a kind of relation that kinetic energy of a wave is proportion. That is, kinetic energy is sort of energy. That energy is proportional to the intensity of the incident light. So if we have increased the intensity of the light, there should have been more kind of photoelectrons emitting out of it. There should have been more kinetic energy present inside the electrons. So with the increase of intensity, there should have been increase in the kinetic energy, but that was not the case. Experimentally, it was observed that kinetic energy is independent of the intensity of the light. So there was a failure in the classical mechanics. We said that kinetic energy is proportional to the intensity, but experimentally it was observed that kinetic energy is not proportional to the intensity, but in fact it is proportional to the what you call as the frequency. And there was a basic assumption, which was, this experiment was done by, furthermore illustrated and explained by Einstein, who considered the basic assumption of Planck that a photon, which was considered earlier to be a wave, he considered this in his experiment. He assumed the Planck's postulate that a photon is considered to be a kind of particle having some kind of energy inside it, which is called, he called as it quanta. This energy is given to be equal to h multiplied by nu, that is the frequency. That means if you increase the frequency for a specific radiation, there will be an increase in the energy. That is, energy is proportional to the frequency of the emitted radiation. More the frequency, more will be the energy present inside it. And he considered this to be of quantized nature, that it is behaving as a particle, and he called it as a quanta. The quanta of photon, the particle of photon, the particle of light, possessing the energy h nu. So on the basis of this very assumption, he concluded that the light is not only a wave, it is acting like a particle also, because it's only possible for a particle to behave, having a behavior like this, having kinetic energy, increase in the kinetic energy with the increase in the frequency. So this is only possible if we consider the particle nature of that very photon, not the wave theory, because wave theory could not explain the kinetic energy increase with the increase in frequency, because it is experimentally seen that it's independent of the intensity. So this was the second thing, which was the failure of, where we see the failure of the classical mechanics. Few other things were, many other experiments were done. One of that is the optical spectrum of elements or different kind of substances. The optical spectrum of some elements. If we consider, there were experiments done that if a body, any kind of substance, it can be metal, non-metal, any kind of thing, if it is heated, if it is given a temperature, if its temperature is increased, then for any temperature greater than 0 Kelvin, that is for any temperature greater than the absolute 0, there will always be a kind of emission of radiations from this very substance if its temperature is greater than 0, which is always possible, and it is an experimental fact. So the emission of these kind of radiations, if for any specific substance, if the radiations are put onto, and these are put onto a grating, diffraction grating. Diffraction grating is a substance which through which we make an incident beam of radiations, and this very thing, they classify this very beam into its constituent frequencies or wavelengths. If this very bunch of photon is having certain kind of frequencies, different kind of frequencies, if we pass this very beam into a grating, diffraction grating, it's having some grooves inside it. If it's passed through the grating, there will be a kind of diffraction inside this radiation beam. So there will be the separation of various kinds of frequencies which are seen on the screen here. There will be a kind of the separation of spectral lines having different kinds of frequencies, like this is frequency psi I, nu j, something like that. So when this very substance is put under some kind of potential or some kind of external field, say E, there will be always a radiation inside it, because we know from the classical wave theory, from the classical theory of electromagnetic radiations, that whenever a charged particle, say electron, is put inside an external field, there it will be exhibiting, if it is exhibiting a motion, for example, say if an electron is considered inside an atom, definitely it is possessing some kind of motion inside it, so there will be a kind of radiation. Okay, it is having some kind of frequency, and that very frequency is proportional, this very frequency is proportional to the periodic motion exhibited by the electron. Okay, so it depends upon the periodic motion, and every periodic motion has its own frequency, which is the fundamental frequency for that particular particle. Fundamental frequency for that particular particle. And classical mechanics says that, classical wave theory says that the frequency which is given out, the total frequency is given as to be equal to the integral summation of linear sum of the fundamental frequencies. If this is having some kind of nu1 fundamental frequency, nu2 some other kind of fundamental frequency for other particle, nu3 for fundamental frequency of some other particle inside that very substance, then the frequency, the overall frequency, is given by the integral multiple between this fundamental frequency. The total frequency is given as the linear sum of these nu2 n3 nu3. This is given by the classical wave theory. So there should have been a kind of total frequency given out on this side, which should have some kind of form like this, that nu should have been of this form, which is observed here. But there was experimentally, it was observed that there is nothing, no kind of frequency which could be seen here which is having the form like this. So the frequencies here were totally different from that very thing which could have been explained on the basis of wave theory. So definitely there was some need of some other theory other than classical wave mechanics. Classical wave mechanics. And these you will see in the further lecture, in the upcoming lectures, that these kind of things will be explained only if there will be considered the particle nature and the quantum nature of those very electrons, of those very photons, of those that very light. So these all kind of experiments will only be considered, or will only be explained on the quantum behavior, if we consider the quantum behavior of the particles, if we consider the quantum behavior of the light. And furthermore, you will see the Compton effect as well, which is a great experiment which was done, the Compton effect. This very thing is similar to that of the photoelectric effect. Photoelectric effect and Compton effect is to somewhat extent they are similar, except a few things. So both of these consider the particle nature of the light. The basic postulate for these very experiments was that photon, that is the constituent particle of the light, is exhibiting a quanta of energy which is as nu. So that very was the basic postulate and was a kind of origin of the quantum mechanics. So in the upcoming lectures we will be seeing the different kinds of theories which were given in explaining all of these kind of things. So we will see in the upcoming lectures how these explain the quantum behavior of this energy and matter interactions. So we will see upon We'll look upon those very things in the upcoming lectures. I think this is enough for today. I will see you in the next. Thank you.